So now we're going to start looking at motion in two dimensions as opposed to motion in one dimension. Recall that one-dimensional motion. We have a car speeding up, slowing down, changing its direction, and even if it went this way and then turned around and came back this way, it was only moving in one dimension. It was only moving in X. With our free fall problems, even if something was thrown up and came straight back down, it's only moving in the Y. It's not moving in the X and the Y at the same time. And that's what we're going to start doing here. And we start off with the simplest problem where we have a ball that is rolling off of a table or a cliff or whatever, and it's going to move this way. And you know that it's going to move something like that. Well, it is moving forward, which is the X direction, at the same time that it is moving downward in the Y direction. And we need to examine those motions separately. Now, the one good thing about examining the motion separately is that all of these formulas still work. Whether you're talking about the motion in the X or in the Y, we use all of the same formulas. It's just a question of how we apply them. So let's go through this step by step. The marble's initial velocity in the Y direction. Well, the ball started off only with horizontal motion. That would be the X direction. The ball at the start of our problem is not moving this way because it's on the table. So the ball's initial velocity in the Y is 0 because it starts off all horizontal or all X. Now, as soon as it gets off the table and it's through the air, gravity is going to change its motion this way. Gravity only works in the Y direction, and it will work in the Y direction. Well, what's the acceleration of the marble in the Y direction? It's going to be negative 9.81 meters per second squared. We'll assume we're going to make down negative for these problems unless we change it otherwise. We know that gravity is what's going to cause it to move this way and accelerate it this way, that Y direction. And we know that that acceleration due to gravity is that right there. Now, what's the acceleration of the marble in the X direction? This one takes a little bit of discussion. Think about this marble with no engine. As soon as it leaves the tabletop, it's moving this way. Is there anything to make the marble speed up going this direction? No. It doesn't have an engine, and gravity doesn't work this way. Gravity only works this direction. So the marble coming off the table has an acceleration of 0 in the X direction. There is nothing to change the velocity of the marble going this way. Going this way, gravity is going to change its motion in the Y, but not in the X. That's a very important note to make, and that's always going to be true about these problems when we have two-dimensional motion of an object flying through the air. Now, how far will the marble move in the Y direction? Well, it's going to move down until it gets to the ground. How far is that? It was given as 1.5 meters. So that is my distance in the Y direction. Now, this says calculate the time it takes the marble to move in the Y direction. Calculate how long does it take to move that 1.5 meters. This is a calculation problem. And we come to our formulas up here. So we want to know the time. If we look at this formula right here, do we know the distance it's going to fall? Yes, it's 1.5. Do we know the initial velocity in the Y direction? Because we're talking about a Y distance. Yes, that initial Y was 0. Try to find the time. I know G. I can solve for T. So here we go. The D, notice I put a little subscript of Y because remember, this is two-dimensional motion. We're going to have a distance in the Y and a different distance in the X. So I need to note that in my formula. The distance in the Y, the initial velocity in the Y, and G is the same. So my distance in the Y was 1.5 meters. My initial Y velocity was 0. I'm going to write the letter G because I know that's 9.81. T. When I do the math with those numbers, I get a time of 0.55 seconds. You can see my math here on the calculator to confirm that you can indeed get that answer. Now, calculate the y velocity when it hits the ground. Let me go over here. I need a final velocity as it gets over here to the ground. So let's see. I know g. I now know the time. I want to find the final velocity. I know the initial velocity. So I can use this formula here. I'll use g equals vf minus vi over t. The g is 9.81 meters per second squared. Final velocity in y minus initial velocity of 0 divided by, we now know a time of 0.55 seconds. My final velocity in the y dimension, y direction, will be 5.4 meters per second. You can see how I did the math there on the calculator. Now, we're given the velocity in the x direction now is 2 meters per second. When it leaves the table, that's the velocity in the x dimension. It says calculate how far away from the table it will land. Well, that is a distance. Remember that we said the acceleration in the x direction is 0. There is no acceleration in the x direction. And of all of these problems up here, the only one that we can use when we don't have an acceleration is this one. And you might have been wondering with our free fall problems and previous problems, like, why do we even have this formula? It doesn't seem like we're going to use it that much. Well, now we are, because we've got a situation where there is no acceleration. So to find the distance, if I know the velocity and the time, I can use this formula. It's an unaccelerated motion, and it only works for the x. We can't use this formula in y because gravity causes an acceleration. So I can go velocity in the x, distance in the x, and time. Notice I didn't put a subscript of x or y with the time, because the time is the same when it's moving in x and it's moving in y. It's the same time for x and y. It's not like it stops moving in x before it stops moving in y or vice versa. So I can use this formula, 2 meters per second. How far is it going to go? The time is 0.55. And there you can see how I got that answer of 1.1 meters. Now to talk about the resultant velocity. Remember, this object has a velocity in x and it has a velocity in y. So when this ball hits the ground, it's going something like that. It's moving in the x and in the y at the same time. But the ball's physical or resultant velocity is that there. The question, what is that value? Well, this now becomes a Pythagorean theorem type of situation because we've got a right triangle because the x and the y work at a right angle to one another. We know the Vy when it hit was 5.4. We know the Vx was 2. We can do a squared plus b squared equals c squared, which is my resultant velocity. And there you can see the final or the resultant velocity of 5.8. So that's how the ball is moving when it's hitting the ground. It's moving, it impacts the ground with a velocity of 5.8 meters per second. So let's graphically represent those vectors. We're going to draw the x and y velocity vectors, and I put a couple points on there. To start off with, it only has an x velocity. I'm not going to even draw a y velocity vector because there isn't one. When it starts off, it's only going horizontal. Well, a few seconds later, it does have a y velocity. But I'm going to say the x velocity is still a little bit bigger. The x velocity is constant at 2 meters per second because remember it's not accelerating this direction. So notice I draw the arrow the same size here because the x velocity vector stays the same. But now we've started to accelerate in the y, so I got a little bit of y velocity now. Well, at some point over here, my x velocity is the same, but now my y velocity has continued to get bigger. Now it's going to be at least the same size as the x. When it hits the ground, the x velocity is still the same size arrow because it is constant. There's no acceleration. But when it impacts the ground, remember that that final y velocity was 5.4. We're going to draw a much bigger arrow to represent that velocity vector now, because now the y is so much bigger than the x. All right, now the next situation, we've got a marble that rolls horizontally off the top of a table that is 1.5 meters high, so the table is the same height. It is still going horizontal. So what's the marble's initial velocity in the y direction? It's still 0 because it starts off horizontal. What's the acceleration in this direction? Well, that's still caused by gravity, so my acceleration in the y is still going to be that 9.81, negative 9.81. What's the acceleration of the marble in the x direction? Well, remember, once again, this thing gets launched, and once it gets launched, it has no rocket engines, and gravity doesn't work this direction, so in the x, the acceleration is still 0. Notice we've got some things that are in common here from the previous problem. How far will the marble move in the y? Well, it's still going to fall to the floor. Its distance that it's going to fall is 1.5. Calculate the time it takes the marble to move in the y direction. Now, if we think about this, everything was the same from the first problem. The y dimension in this problem didn't change, so it's going to be the same time because it's still falling 1.5 meters and it's still being accelerated by gravity. It still had an initial velocity of 0, so the time it takes it to fall is still going to be what we already calculated. Calculate the marble's y velocity when it hits the ground. It's going to be the same thing. It's going to be that 5.4 meters per second that we already figured out because nothing changed in the y direction. So our answers are going to be the same. Now here's where the problem gets different. Now we're saying if the marble was rolling 5 meters per second as opposed to it was rolling off at 2 meters per second in the previous problem. Calculate how far away from the table it landed. So now, if this marble was going faster this direction, we know it's going to land further out here than it did before. Before, we got a distance of 1.1 meters. We should get a number that's bigger than that because it's coming off the table faster. Well, let's do the math. We can use this problem because that equation because there is no acceleration. The only time you can use that formula to calculate a velocity, distance, or time is if there is no acceleration, and there is no acceleration in the x dimension. So what was my velocity in the x? Was now it's 5 meters per second. I want to know how far it goes, but it still only moves for 0.55 seconds because the time is determined by gravity. And this thing stops moving forward when it stops moving down or when it hits the ground. I can take my calculator and I can do 5 times 0.55. 5 times 0.55. I get 2.75 meters. And that makes sense with what we already kind of reasoned out, that if the marble leaves the table faster going this way, it's going to wind up further this direction than it did before. And it's now going to wind up 2.75 meters this way. Now the resultant velocity has a velocity in x and it has a velocity in y. The velocity in x is 5. We know that when it hits the ground, it's going to have that final velocity of 5.4. So I can do an a squared plus b squared equals c squared and find out what the resultant is. My resultant velocity is now 7.4 meters per second squared, which is a lot more than what it was in the first problem. Because now, even though my y velocity is still the same, my x velocity is a lot bigger, so it makes that resultant number a lot bigger or a lot higher. So as for drawing the vectors graphically with an arrow, I wanted to make this a little bit bigger than I did in the last problem, because in the last problem my velocity was only 2. Now I'm going to call it 5. So I'm going to draw a bigger arrow. Still not drawing a velocity vector for the y up here because it has no initial y velocity. Here I'll make a bigger arrow. Now I've got a little bit of a y velocity. There's my same size x velocity vector. The y is a little bit bigger because it is accelerating this direction. When I impact, there's my same size velocity x, which is 5 meters per second. My y velocity. Question, should I draw my vector bigger or smaller than that one? Well, go back. Remember, the final y velocity is 5.4 versus our 5. So I want to draw my y velocity vector a little bit bigger. Something like that. But notice in the first one, where the x velocity was 2, the y was a lot bigger than the x. Here, they're pretty close to the same number, so I'm going to make my arrows somewhat similarly sized. All right, now number 3. Marble rolls horizontally on the table. Now it's a 3 meter tall table as opposed to a 1.5 meter tall table. Marble's initial velocity in the y is still 0 because it is just coming off horizontally. In other words, it's only moving in x. It's not moving up and down at all. The acceleration is still going to be negative 9.81 meters per second because even though the table is taller, it's still gravity that's going to pull it to the ground, and gravity still accelerates an object at negative 9.81 meters per second. The acceleration of the marble in the x is still 0. There is no acceleration in the x direction because there's no rocket and there's no gravity that works this way. The motion is going to be constant in the x direction. How far will the marble move? It's going to be 3 meters. Now this says calculate the time it takes the marble to move in the y direction. Well, when we did that for 1.5 meters, we used this formula here, and the same formula will work. We just have to change the distance now. Instead of 1.5, we're going to change it to 3. So here's my time. Now it's 0.78 seconds, and you can see how I did my math there. Now, does that jive with what we did before? Before, it only took 0.55 seconds, but the table was a lot shorter. So now that the table is taller, yeah, it's going to take more time for it to move to the ground. Our new time is 0.78 seconds. I can use this same formula here to calculate the final y velocity because I know 9.81, final velocity in the y, the initial velocity in the y was 0, and now we know a time of 0.78. Now my final velocity in the y, final velocity in y is 7.65 meters per second, which is faster than the 5.4 we found before. Because now the table is taller, it is going to be going faster when it impacts the ground. So that number makes sense. So to calculate how far away from the table it landed, the x direction distance, remember that we can use this formula in x because there is no acceleration. We can't use this formula for y. We can only use this for x. The velocity in the x direction, I went back to that original number of 2 meters per second. Distance in the x, but now the time is 0.78 seconds. So I have 2 times 0.78 equals 1.56 meters. So the marble was going at the same speed as it was in number 1. And in number 1, it went to a distance of 1.1 meters. But now it went to a distance of 1.56 meters. Well, why is that? If the x direction motion didn't change, it's unaccelerated and it starts off at the same speed, what's the difference? Well, the difference is it had more time to move this way because the table was taller. Now the resultant velocity, once again, you have an x velocity and you have a y velocity. The x velocity in this case was 2 meters per second, but my y velocity is now 7.67. We'll do a squared plus b squared equals c squared to get that resultant velocity. And that resultant velocity is going to be 7.92 meters per second. You notice that number is a lot closer to the y velocity than the x velocity, and that kind of makes sense because the y velocity is a lot bigger than the x. To graphically represent, I'm going to go back to that little bit smaller arrow for x because now it's 2 and not like 5. Still no initial y velocity, so I don't need to draw an arrow this way. Still 2, a little bit of y now. Same size arrow because the x velocity is not changing. Maybe now the y velocity is a little bit bigger than the x. And when we get to the end, I'm going to run out of paper, but I'm going to draw this as big as I can because now the final y velocity is over 3 times as big as the x because now it is falling farther. All right, some key points to take away from all this. First of all, that time is determined by the y motion. So when you get to any kind of these problems, you need to find the time. The time is determined by how long does it take gravity to move it a certain distance. Acceleration in the x is 0 because there's nothing to accelerate it in the x dimension, only in the y. The time in the x is the same as the time in the y. There is only one time. You can use this formula only in x because that is the dimension of motion where you don't have an acceleration. The final hint here is solve everything x and y separately. You have to approach these problems looking at just x and just y by themselves.